In mathematics, Pascal's triangle is a triangular array of the binomial coefficients. In much of the Western world, it is named after French mathematician Blaise Pascal, although other mathematicians studied it centuries before him in India, Persia, China, Germany, and Italy. The rows of Pascal's triangle are conventionally enumerated starting with row n equals 0 at the top. The entries in each row are numbered from the left beginning with k equals 0 and are usually staggered relative to the numbers in the adjacent rows. Having the indices of both rows and columns start at 0 makes it possible to state that the binomial coefficient appears in the nth row and kth column of Pascal's triangle. A simple construction of the triangle proceeds in the following manner. In row 0, the topmost row, the entry is. Then, to construct the elements of the following rows, add the number above and to the left with the number above and to the right of a given position to find the new value to place in that position. If either the number to the right or left is not present, substitute a 0 in its place. For example, the initial number in the first row is 1, whereas the numbers chapter 1 and 3 in the third row are added to produce the number 4 in the fourth row. This construction is related to the binomial coefficients by Pascal's rule, which says that if then for any non-negative integer n and any integer k between 0 and n, Pascal's triangle has higher dimensional generalizations. The three-dimensional version is called Pascal's pyramid or Pascal's tetrahedron, while the general versions are called Pascal's simplices. History. The pattern of numbers that forms Pascal's triangle was known well before Pascal's time. Pascal innovated many previously unattested uses of the triangle's numbers. Uses he described comprehensively in what is perhaps the earliest known mathematical treatise to be specially devoted to the triangle, his Traité du triangle arithmétique. Centuries before, discussion of the numbers had arisen in the context of Indian studies of combinatorics and of binomial numbers and Greek study of figure-8 numbers. From later commentary, it appears that the binomial coefficients and the additive formula for generating them were known to Pingala in all before the 2nd century BC. While Pingala's work only survives in fragments, the commentator Varahamihira, around 505, gave a clear description of the additive formula, and a more detailed explanation of the same rule was given by Haliade, around 975. Haliade also explained obscure references to Meru Prastara, the staircase of Mount Meru, giving the first surviving description of the arrangement of these numbers into a triangle. In approximately 850, the Jain mathematician Mahavira gave a different formula for the binomial coefficients, using multiplication, equivalent to the modern formula. In 1068, 4 columns of the first 16 rows were given by the mathematician Bhattacharya, who was the first recorded mathematician to equate the additive and multiplicative formulas for these numbers. At around the same time, it was discussed in Persia by the Persian mathematician Al-Khariji. It was later repeated by the Persian poet astronomer mathematician Omar Khayyam. Thus the triangle is referred to as the Khayyam-Pascal triangle or Khayyam triangle in Iran. Several theorems related to the triangle were known, including the Binomial Theorem. Khayyam used a method of finding nth roots based on the binomial expansion, and therefore on the binomial coefficients. Pascal's triangle was known in China in the early 11th century through the work of the Chinese mathematician Jia Jian. In the 13th century, Yang Hui presented the triangle and hence it is still called Zhang Hui's triangle in China. In the West, the binomial coefficients were calculated by Gersonides in the early 14th century, using the multiplicative formula for them. Petrus Apianis published the full triangle on the frontispiece of his book on business calculations in 1527. This is the first record of the triangle in Europe. Michael Stiefel published a portion of the triangle in 1544, describing it as a table of figure-8 numbers. In Italy, Pascal's triangle is referred to as Tartaglia's triangle, named for the Italian algebraist Niccolò Fontana Tartaglia, who published 6 rows of the triangle in 1556. Gerolamo Cardano also published the triangle as well as the additive and multiplicative rules for constructing it in 1570. Pascal's Traité du triangle arithmétique was published posthumously in 1665. In this, Pascal collected several results then known about the triangle, and employed them to solve problems in probability theory. The triangle was later named after Pascal by Pierre-Raymond de Montmort, who called it Table Theorem, Pascal Paul les Combinaisons, and Abraham de Moivre, who called it Triangulum Arithmeticum Pascalianum, which became the modern Western name, Binomial Expansions. Pascal's triangle determines the coefficients which arise in binomial expansions. For an example, consider the expansion 2 equals x2 plus 2xy plus y2 equals 1 by 2y0 plus 2 by 1y1 plus 1 by 0 y2. Notice the coefficients are the numbers in row 2 of Pascal's triangle. 1, 2. In general, when a binomial like x plus y is raised to a positive integer power, we have n equals a0 xn plus a1 xn minus 1 y plus a2 xn minus 2 y2 plus and minus 1 xyn minus 1 plus n, where the coefficients I in this expansion are precisely the numbers on row n of Pascal's triangle. In other words, this is the binomial theorem. Notice that the entire right diagonal of Pascal's triangle corresponds to the coefficient of yn in these binomial expansions, while the next diagonal corresponds to the coefficient of xyn minus 1 and so on. To see how the binomial theorem relates to the simple construction of Pascal's triangle, consider the problem of calculating the coefficients of the expansion of n plus 1 in terms of the corresponding coefficients of n. Suppose then that now the two summations can be reorganized as follows. We now have an expression for the polynomial n plus 1 in terms of the coefficients of n, which is what we need if we want to express a line in terms of the line above it. Recall that all the terms in a diagonal going from the upper left to the lower right correspond to the same power of x, and that the a terms are the coefficients of the polynomial n, and we are determining the coefficients of n plus 1. Now, for any given I0 or n plus 1, the coefficient of the xi term in the polynomial n plus 1 is equal to I plus I minus 1. This is indeed the simple rule for constructing Pascal's triangle row by row. It is not difficult to turn this argument into a proof of the binomial theorem. Since n equals bnn, the coefficients are identical in the expansion of the general case. An interesting consequence of the binomial theorem is obtained by setting both variables x and y equal to 1. In this case, we know that n equals 2n, and so in other words, the sum of the entries in the nth row of Pascal's triangle is the nth power of 2. Combinations. A second useful application of Pascal's triangle is in the calculation of combinations. For example, the number of combinations of n things taken k at a time can be found by the equation, but this is also the formula for a cell of Pascal's triangle. Rather than performing the calculation, one can simply look up the appropriate entry in the triangle. For example, suppose a basketball team has 10 players and wants to know how many ways there are of selecting 8. Provided we have the first row and the first entry in a row number 0, the answer is entry 8 in row 10. 45. That is, the solution of 10 choose 8 is 45. Relation to binomial distribution and convolutions. When divided by 2n, the nth row of Pascal's triangle becomes the binomial distribution in the symmetric case where p equals 1/2. By the central limit theorem, this distribution approaches the normal distribution as n increases. This can also be seen by applying Stirling's formula to the factorials involved in the formula for combinations. This is related to the operation of discrete convolution in two ways. First, polynomial multiplication exactly corresponds to discrete convolution, so that, repeatedly convolving the sequence 0, 0, 1, 1, 0, 0, with itself corresponds to taking powers of 1 plus x, and hence to generating the rows of the triangle. Second, repeatedly convolving the distribution function for a random variable with itself corresponds to calculating the distribution function for a sum of n independent copies of that variable. This is exactly the situation to which the central limit theorem applies, and hence leads to the normal distribution in the limit.